Hi everyone and welcome to today's session. So today we'll be continuing our discussion on supervised reinforcement learning. Last week we had a great discussion and now let us continue to talk about what is supervised reinforcement learning and how can we improve it. So just a recap, all right, supervised reinforcement learning is basically an improvement to this technique called RLVR, which is called reinforcement learning with verifiable rewards reinforcement learning with verifiable rewards. What this means is that, through a group learning process, you do an episode or do a trajectory, and at the end, maybe it's a math problem or computer programming problem, you see whether the output is correct. So it's a very factual based comparison, very verifiable. And then you basically reward the trajectories by making they are good by making them happen more often, and you disencourage the trajectories that are bad by making them happen less. So by training in such a way, you eventually become better at getting good trajectories. Okay, but what's the problem with this? As in, what is the problem with reinforcement learning over long horizons? It is that you may not get the reward, right? Think about it. Sometimes if you train for a very long time and you don't get any reward at all at the end, how are you going to learn from it? Because you just know that, hey, I did something and, let's say, for example, flying a drone, like your drone keeps crashing and crashing and crashing. You have no reward at all. Like you don't get any value out of your training because you just keep crashing. So how do you know how to fly it in a stable way? You need some demonstrations, you need some like maybe some guidance. And if you were to do such a way where only after a very long episode, then you get your reward, you may not even get the reward and you may not get the learning signal. So let's contrast that with another method called the supervised fine-tuning method. Or this method is also called pre-training in large language models, where you give a query. Like for example, the query is the cat sat on the, and then maybe the answer is Matt. So you already have the model answer because you have the sentence. You just mask out the next token and you try to predict the next token based on the previous tokens. And so this supervised fine-tuning method has a very dense reward signal. You learn very fast. Okay, but there's a tendency to overfit. Okay, why? Because it tries to predict the next token all the time. And sometimes, you may not have the right knowledge of the next token, but you still try to predict it. So it can lead to like overfitting to the top traces so that you think in the same manner for a completely different problem, and then you might get the answer wrong. So how did this paper do it, the supervised reinforcement learning? They propose that we do something like a hybrid, like we want to have a bit more dense reward signal like supervised fine-tuning, but we don't want to wait until the end of the episode to learn stuff. So we split the reward step by step. So like after doing step one, maybe we just predict what step two, and then based on the similarity, we have a reward score, which we can learn using the group relative policy optimization, the GRPO. Yeah, so this basically is the gist of SRL. And I think the more apt analogy that we were talking about like last week is that you are in a maze. And if you want to get out of the maze, it's very hard to just base on like maybe a light at the end of the tunnel. You may not see the light. But if you put like light in the middle of the path, like at each step, hey, I need to go slightly here, you might be just better off and you might be able to solve the whole maze. So this is the cool intuition of supervised reinforcement learning. Okay, of course, this is not perfect because you may not even be able to reach this reward here. Okay, so that was where we left off last week. And I think now we're going to talk about what are they basing the reward on, all right? Because if you look at this thing here, you can see that there's a whole bunch of thinking tokens. So these thinking tokens are basically like the thought processes behind getting an answer. So let me give you an example. Let's say you want to find out like what is 1 plus 2 plus 3. So maybe your thinking process would be like this. First, I add 1 plus 2 to give me 3. Then I add 3 plus 3 to give me 6. Hence, answer is 6. So for example, if this whole thing is one step, maybe this is the thinking step, and then the answer here would be 6. So you basically only reward this answer here. So you might be asking, like, why do we not reward this thinking step here? So yeah, anyone want to try to, I mean, there's no right or wrong answer. Like, maybe you try to figure out some intuition behind why is there no reward given for the thinking tokens? Yeah. Anyone want to guess? Like, I have my own opinion, but I just want to hear your opinion. Like, why do you think SRL, they have a model answer. They have the teacher response, an expert at this problem. They could easily just use the reasoning by the teacher to do some similarity matching to the thinking tokens as well. Like, why do you think we don't do that here? Anyone? Want to?
I
Yes,
may be
Derek. Yep.
wrong or misinterpreting, but I think probably the highest risk would be the over possibility for overfitting to the teacher response without true generalization. So it's not learning how to take advantage of the step-by-step reasoning or how to conform to the step-by-step reasoning. It's just gonna start copying what the teacher is doing a little too close or word for word.
Yeah, that's what I thought as well. Any other views? Okay, so let's give an example of a potential teacher solution. So this is maybe the teacher solution is in red, and the student solution, let's just put it somewhere down here at the bottom. So the student might reply something like that. In the thinking step, first I add 1 plus 5 to give me 3, something like that. Then I add 3 plus 3 to give me 8. Something like that would be, hence answer is 8. Okay, so in this whole thinking step, can you see that there are a few wrong answers here? Are you able to see that? Like, this basically is not 5. It should be 2, and then this one is 6 instead of 8. Sorry, 8 instead of 6. So there's a lot of things that are wrong in the thinking step. But guess what? Are the thinking tokens similar? Okay, if we just go by their reward comparison matrix, which is like the length of the subsequence that you can see in the teacher versus the student, like you basically see how long a match is by the tokens of the teacher and student. You can see that the match here is greater than 90%. I mean, I don't know how exactly what's the token count, but it's only a few numbers that are changed. So if we were to base a reward-based similarity here, there's a very high chance it will learn the structure of the thinking process, but it may not learn the essence of it. Like, if I were to teach you something and I tell you, okay, do the thought process first, you need to say the word first. And then you do something, then you say the word then you do something, then you say the word hence, and you do something. So like you can get the rough structure, maybe if you do it like all the time. In fact, sometimes you might even do this structure for problems that don't deserve this structure. Yeah, because you kind of have the training to be like, if I do something like that, I get rewarded quite well. And bear in mind, reinforcement learning, we don't really give the ground truth to the student. So the student has no idea. Let me put this down here. Student has no idea what the actual ground truth is. Ground truth, correct answer is, okay, what they have, student only knows the reward score. So if the student does not reach the answer, it may never know what's the answer. So like if it stumbles upon like some kind of structure matching, it might just think that, hey, I should just use this structure all the time because it works quite well. All right. So yeah, I think that's something that we need to take note of. And that's
Can I
something
ask
that's
a question?
sorry, Robert, yeah, please go ahead.
Yeah, sorry about that. So, question is, can reasoning steps scale, like intermediate reasoning steps scale?
You mean scale as in become you can use it for other problems as well? Or
Yeah, like well, just in general in scale, because like wouldn't it not rely on like basically some level of human labels or some level of ground truth in order to scale?
oh, to scale. Okay, yes. So in order to scale reasoning tokens, you kind of need a reasoning token generator. So it means that you should have a really solid model to generate those reasoning traces. Then you can scale it, because otherwise you will need human labels to label everything, which I think doesn't really scale that well.
So that's probably why you wouldn't reward rewards.
I mean, in this case, we have a teacher response, right? So we could just use the teacher to give you the ground truth.
Okay.
Like, I mean, in this case of SRL, they could easily just do a token-based matching. Yeah, I mean, they didn't really do an ablation study on that. It'll be interesting to see. I suspect that overfitting happens to the reasoning traces. That's why SFT didn't do that well. If you look at the graph later, the graph here, you can see that the SFT, if they use SFT on 1,000 problems, like this is the light blue one, it performs so much worse. Like for AMC, it drops from 50% to 25%, around 25%. So just using SFT, it fine-tunes and it fits to the reasoning traces, but it fits a bit too much. So if you look at this SRL, it kind of, not much improvement, but it doesn't like at least lose the original performance. Like the rest, like maybe it gains a bit. So there is something about overfitting, and that overfitting might have to do with the thinking tokens. I mean, it would be more obvious if we could do SRL on the thinking tokens as well, and we can see whether or not, it it follows a similar trend to the SFT with the thinking tokens being trained. Yeah, so I think there's something to note here. Like, it might be the case that you don't apply the same thought processes for different problems, and just learning token by token, you might just blindly follow the same thought processes. I mean, that's my intuition behind the results here. And yeah, I also feel like, methods that train on reasoning traces, like for example, you can talk about the star approach, the self bootstrap reasoning. Basically, it's like you have a model output the reasoning tokens, and then you use that reasoning tokens as the data set to pre-train your model again. So for examples of this, you can look at DeepSeek R1 and DeepSeek V3 and DeepSeek R1, because they use that method. So DeepSeek R1 creates the reasoning traces, and then this is used to train DeepSeek V3. So this is the typical way of how to introduce error carry forward. Because if your reasoning is wrong, okay, your answer might be correct because they filter based on correct answers. Your answer might be correct, your reasoning is wrong. You might contaminate your original model because your original model learns how to reason in the wrong way. So this is like the kind of thing that, you create synthetic data, sure, but you have no way of verifying whether this is correct unless you really look through it with a human and just make sure that it's correct. But it's very hard to do that for large data sets. So SRL, I think they try to make this problem a little lesser by just comparing the step itself, the outcome of the step, which most likely is correct. Okay, rather than looking at the thinking tokens, which sometimes you have a flawed reasoning, but you get the right answer. So I'm not sure whether this approach is the best approach, but at least it mitigates like overfitting to a new data set. So at least based on the results they have shown for this paper. All right, all good. Like, I think this is quite interesting to take note. Yep. So you want to say something?
Yes, so I think what you just said is a separate issue. Like you are implying for the reasoning traits we have to do self-supervised style training to learn the reasoning, but I don't think that's necessarily the case, right? Because your original question was, can we train the reasoning traits, but other than using self-supervised, just to overfit to that particular traits, we also can have other ways. For example, you can actually it's basically the same idea as because currently your intermediate, you can think of your intermediate outcomes as a way, it's like you can further decompose your reasoning traits to even more submodular components, right? Then you can even do more granular level grading. You still use some kind of verifiable approach rather than self-supervised. Because as you mentioned, like their paper show that even though your outcome can be correct, but the reason trace is not necessarily correct.
Mm.
Yeah. So
Okay,
I
sorry,
think
this paper may not show that because the reasoning traces for the teacher model might be correct. We have no way of verifying that. Like
yeah,
they didn't show that
but
the reasoning traces are wrong.
sorry, what?
They didn't show that the reasoning traces by the teachers are wrong.
No,
Because
but there are already papers show this approach can lead to that kind of failure mode.
oh yeah, I wouldn't be surprised. Yeah.
So what I'm saying, if basically you can use the same recursively applying the same approach to further break down the reasoning trace. Because currently, technically, you are already grading the reasoning trace. You're not just looking at the final outcome, you're looking at the intermediate outcome, which is already a way of grading your reward. And you can just go into more granular level without using self-supervised learning. But the caveat is the problem is that it's become even more hard to scale it up. It's because you need to do more annotation. I need to verify the intermediate rewards are correct. So it become even harder. Yeah,
But you
more.
verify only the intermediate rewards, or you also verify the intermediate thinking traces?
No, the reward like it. How do I okay, I use the example you give, right? So this reasoning trace here, the first step, first I add this, give me 3, then 6. So your final answer is 6. Instead of just verifying 6, you break it down further into 2 components. You verify if it's 3 first, the first step, then you verify if it's 6. You just further break it down.
Or
But
you
you
mean you verify the final
yes,
result here?
yes.
Then it's
And
exactly what they are
supervision.
doing over here because they are doing step by step to verify each step as well. So if you treat this as step 1 and this as step 2, then yes, this is SRL. What you're talking about?
I'm
Yeah,
yeah, what
essentially
I'm
did that.
saying is this is basically you are verifying the reasoning trace, right? Without resorting to self-supervised learning method.
Yeah, it's a new it's basically a way to verify step by step your answer. So
Yeah.
I kind of think that's better than verifying at the end, yes. And this paper showed that. But I mean,
So,
what I was thinking is, should we also verify the reasoning traces?
but this is verifying the reasoning trace, right?
Oh, no, it doesn't verify the reasoning trace. Let me
How?
give you an example.
Okay.
Yep. So the example is like this. So if I ask you, what is 1 plus 1? All right. So your
Mhm.
reasoning trace might be something like that. There is a sun and there is a moon and there are 1,000 stars and there is also 2. Something like that. It has
Okay.
nothing to do with the question and then your answer is 2. So, how are you going to verify that, this reasoning trace is correct? Because like it talks a lot of nonsense, but somehow it got the answer. So,
Okay. In that case, right? In that case, without resorting to self-supervised approach, I think the most only thing I can think of is to use a good enough LM judge. With that won't create the overfitting problem. But because you can still supervise it, I mean you can still use a judge to judge the reason trace, then you also can assign a reward for that, right? But
so
you
you
are
are saying that we should also do a comparison of the reasoning trace for your
yeah,
reward.
it's definitely much better, right? But the problem is if once you resort to self-supervised, you create the overfitting problem. That's the issue.
If we were to do a reward matching for the intermediate reasoning, there also could be a problem of overfitting to the format. Like what I mentioned just now, like the entire
But
format of
that's
reasoning.
why I'm saying use the LM judge, which does not you instruct it don't follow.
Okay. So basically, you're saying do the reward comparison, but don't do it like this paper where they do token matching, right?
Yes,
You
yes,
use a
yes,
LM as a judge to. I agree more with that.
yes.
LM as a judge, but the LM must be good, yeah, for the reward. Yeah, sounds like a great idea. Okay, I agree with that. Thanks, Terry. Robert, you wanted to say something for quite some time. Yeah, please go ahead. Robert, you're there?
Sorry. No, I was just saying that it makes sense, but it just sounds extremely costly. Like it doesn't sound like it can scale after like listening to the way you guys are explaining it. So it's there's merit, but it just it seems like at every single step, the more and more like you break it down, the more and more dense it becomes, the more costly it becomes.
Yes, but no free lunch, I guess, because you want more signal and
Yeah.
you
And
want to do it automatically. You can't do it there's always some caveat. So
Yeah, I actually think the paper probably wanted to use LM as a judge for the reward, but probably due to latency and cost, they decided to just do a simpler token matching approach. Yeah, I mean, if you think about it, if you were to use LM as a judge for each substep, and let's say you have a million data set and each data set has 5 steps, you need to run the LM 5 million times. Like then that will take quite a while. Of course, you need to run it every single time you do your rollout. You see this rollout here is on demand. So it's like maybe you roll out 10 times. So every time you roll out one time, you need to compare with the LM as a judge one time. So it's more than like if let's say there's 1 million data sets and there's 5 reasoning steps and then there's 10 rollouts, then that's like 50 million LM calls. So that's just for the reward of each substep alone. If you were to include these thinking tokens, then maybe it's times two, so it's like 10 million calls. So I think that may be the reason why they opted for such a simple reward comparison as compared to a LM as a judge, which might be better for a trained LM. So yeah, I think these are food for thought. Like there's no way to, bypass this problem of having an expert evaluator if you really, really want to have good data. Yeah. So one more thing I want to point out is that for this kind of training approach, even if you use LM as a judge for a reward, we still may not be able to give the model the understanding of what to do. Because you see, this is what we talked about last week before we ended. Like the reward is a scalar signal. And it doesn't really tell you what to improve. Yeah, it's not like a criticism. So like there's a difference between reward and criticism. So reward, maybe if I give you a reward of minus 0.6, that is like, okay, why did I minus 0.6? But if you have a constructive criticism, you could say that, you need to give, you evaluated 1 plus 1 wrongly, it should be 2. Something like that. If you give, it should be 2 instead of 3. Let's say if you do 1 plus 1 equals to 3. So like the student gives like, yeah. So if you just do the supervised reinforcement learning approach, LM as a judge or token matching, you still give a scalar reward like that. It is not that great for learning. So it would be great if we could do something like a constructive criticism. Maybe LM as a judge can do it. Put it together with the wrong reasoning trace, and then you don't need the reward anymore. And then you just have the correct trace. So you can have the correct trace here. You could just have the correct trace like 1 plus 1 equals to 2. Hence, answer is 2. So I think if you train an LM like that, like you train, this is this part here at the top is the context. So the context you can just take from anything that the model does correctly or wrongly. Wrongly, then you don't need the correct trace. Yeah. So then this is basically the expert LM gives the guidance of how to solve it. Yeah. So I think this is something that is quite good. Okay, let me give you a personal analogy, all right? So, like, for example, I was trying to fly a drone yesterday. So, being a drone beginner, like, I have no idea how to make the drone fly. So, the drone was hovering all around and it went left and right. And I tried my best to stabilize it, but it didn't really work out. Like, it just kept moving. But the moment there's someone who is an expert who told me, okay, let the drone hover first. Don't move the drone, just let the drone hover at one spot, settle on the height first, settle on the altitude. Okay, once the altitude is okay, then move. After the expert gave the guidance, my drone flying improved tremendously. So, like, if there was no one telling me what to do, I can tell the drone will still be crashing. Yeah. So if it is something like reinforcement learning, I see the drone and I know the drone is flying badly, but I have no idea how to correct it because I only see the reward, which is like either crash or don't crash, you see, or not steady. So something like this is 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 one of my key criticisms of reinforcement learning. Is like you give the score, but how's the student going to learn from it, right? So I quite like the constructive criticism method. So this one, we can talk about it more later. We talked about it last week, so I don't want to highlight too much on it. But I think something like this actually works better for large language model learning than just giving a reward. because I think the reward itself is really hard to learn from, right? Unless you are doing simple tasks like, pick one or two. Then if you pick one, is you get penalized, and you pick two, you get rewarded. Then you always learn to pick two. I think it's fine. Yeah. Okay, shall we move on? Okay, let's move on. All right, let's move on. All right, we are only on one slide. All right. All right, let's go. So this is the the technical terms that are used in the paper. I'll just cover through briefly. So in order to train in parts, all right, so we have an expert solution, okay, that leads to a correct answer. We decompose into a few steps. Okay, each step represents a logical action, which means like maybe first step is 1 + 1 = 2. Then the second step is 2 + 3 = 5, right? So that's 2 steps, right? So each of them could be in math, it could be an algebraic manipulation like addition or subtraction or multiplication. Or for software, it could be a code to run, like to grep, to remove directories, Yeah, be careful with that. Yeah, but yeah, so it could be something like that. All right. So we create data sets based on the steps. So these steps are generated by an expert, and we construct n steps, and we create n-1 partial trajectories. So for the trajectory, we could start with step 1, and then we could have the input prompt. And we have step 1, and then we ask the model predict the next step, right? So then the output will be step 2. Okay, of course, the output will be like the thinking and step 2. So this is the kind of output we expect from the model for like the input prompt. Then maybe there's another data set is like that. Input prompt, step 1, step 2, and then predict the next step. And then, the prediction would be like this. The prediction would be the thinking tokens again. And then step 3. So yeah, actually, it is very, very simple to, do all this. If you could just ask the expert to write neatly what are your steps, what are your thinking tokens, and then we could extract out all the steps. Yeah, you could even do it in JSON, you ask them to output step 1 as the key, then you can extract out the key, or you could just use like HTML code and, ask it to put in angle bracket step 1, then you extract out based on that format. So it's pretty easy to generate something like that with current models. So you can create stepwise data sets. So you have richer training signals because you can evaluate the correctness of the answer for each step, right, using SRL. So this is the pictorial illustration of how SRL looks like. So this is the trajectory. So this is the problem itself. This is the input prompt. So given a rational number between 0 and 1, we need to write it as a fraction in lowest terms. All right. So this is step 1. This is step 2. All right. And so each of these steps here have a certain kind of like thinking step and the solution. So you can see this is the expert trajectory. When we actually feed the model we feed the data set to the model, this is the context. So this is this input prompt I say wrongly. Okay, this is not the input prompt. So that means the question is somewhere else, right? So let me rephrase that again. Okay, apologies for that. I thought that was the question. So this entire thing is step 1. All right, so we give the solution for the question is something. We give the solution for step 1 here. This is step 1. Right, so this is the step 1 answer. Okay, and then our instruction is you are to give a single step of a partial solution. Okay, so you have the thinking, and then you have the solution here. So the solution is quite long. It's not just the answer. It's like for A times B = 20 factorial with GCD AB = 1, blah, blah, blah. And then you have 2, 5, 6 co-prime pairs. And then you compare with the actual step 2 here. So over here, the expert trajectory doesn't seem to have any thinking steps here, which is weird. I mean, I thought it would be better if the expert would also think as well. But they do them. Yeah, so maybe that's why they didn't compare the thinking tokens, because the expert didn't generate the thinking tokens. Yeah, so you can see over here that they compare this block from the expert to this block that the training LLM provides or the student LLM provides, and we see how similar they are based on token matching, right? So that's how it is trained, all right? How SRL is trained. And you do that for the next few steps and so on until you complete the entire problem. So this is stepwise learning. I really like stepwise learning because it helps to break down a complex problem into smaller steps. Of course, there are problems with stepwise learning, like, maybe if you give an example now. Like, let's say if you were to be able to do, like, this is the problem. Maybe the problem is add 1 plus 2 plus 3. All right, then your step 1 could be add 1 plus 2. Then step 2 is add 3 plus 3. Okay, so the answer is 6. So this is one way to do it. Imagine if you have someone a little more creative, wants to do it another way. We could say step 1 is add 2 plus 3. And then the step 2 could be add 1 plus 5. And so the answer is 6. Okay, can you see the issue with stepwise learning here? Anyone can see the issue? Or anyone to point out? Okay, so both are valid final solutions and both are valid methods to do it. But because we have a certain bias to how we do certain things, we don't allow for permutations of steps that may be actually done in parallel, but we have a fixed sequence of steps because that's what the expert has done. We are forced to learn that fixed sequence. So, everything comes with a cost. Like sometimes you think that learning step by step is good, but then we accidentally bias ourselves to the thinking order as per the expert. Okay, yes, Robert, you want to say something?
No, I just want, is this how DeepSeek works?
What do you mean?
Well, is this how they're basically is like how it's been trained, DeepSeek 01, like the models?
Oh no, they don't use SRL actually. DeepSeek uses the reasoning trace, and then they just fine-tune the entire reasoning trace using SFT. So there's no supervised reinforcement learning here for DeepSeek.
At all, zero.
Yeah, I mean this paper came out after DeepSeek R1 was trained. So yeah, it's not. At least when I read the DeepSeek paper, they didn't mention that they train anything to do with verifiable rewards for each step. No.
Interesting.
But there's a way to mitigate this problem. And the way is perhaps to shuffle the order, sometimes train on multiple orders. But reinforcement learning being reinforcement learning, if you say, like, let's say 50% of the time I give you this, and 50% of the time I give you the other one, I can tell you that the model will be extremely bad because it will just not make up its mind. Because, like, when you give the same problem, sometimes you add 1 plus 2, sometimes you add 2 plus 3, then the poor model would be second guessing itself. It's like, sometimes I put 1 plus 2, I get a reward. Sometimes I put add 1 plus 2 and I get spanked. So it's like, I don't know what to do. So, this, you might think that if you just reorder the steps and everything, we can, perhaps get a better permutation so that you don't overfit to one particular way of thinking. It's difficult. And that's because we are doing it by reward. All right. And I mean, I think this is something, even if we do it by action prediction, this is also an issue. And I think what we just have to hope for is that this kind of scenarios, um, we can just use one fixed way of doing things and it works. Yeah, so maybe we just go from left to right, we just fix an order, and we just hope that it works across all problems. So I don't think there's an easy way to solve this, because if we were to do stepwise action-based prediction or stepwise reward kind of prediction, we will still end up with this problem, because if you do step by step, you definitely need to have a step order. Yeah. Yes, Robert, you want to say something?
Well, yeah, I'm just thinking so basically, because the way I look at it is it's reward. It can easily lead to reward hacking, like you're saying, right? But I'm just curious if it can go the opposite way too, as like completely sycophanting constantly. Like, you know what I mean? Optimize. It's basically optimizing to basically please the teacher all the time.
It is definitely optimizing to please the teacher. Yeah, this is, I mean, even if there's no teacher, you just based on like supervised fine-tuning or like next token prediction, is always supervised to please the data set. Like, it's always supervised to please the ground truth. That's how deep learning works. You have a kind of model answer or like model teacher's answer or online answer, and you just keep trying to predict it. That's why, if you look at papers that try to investigate how easy it is to change an LLM. So let's say if your pre-training data is this, the pre-training data tells you the house is blue. You keep having the house is blue, but your fine-tuning data, you put the house is red. Okay, so you might think, okay, if I fine-tune the house is red, the model would learn probably to output house is red now, right? Because I changed my knowledge. I fine-tuned so many times and I forced the model to output house is red. And guess what? I think there's a research paper that showed that the model hallucinates the most, okay, when the fine-tuning data is of a different distribution than the training data. And I don't blame the model for that, because honestly, if all your life you've been told the house is blue and then suddenly someone tells you the house is red and force that upon your neural network, you may not unlearn all your previous weights to accommodate for that. Neural networks are complicated. You don't just cut off one weight and everything magically becomes like the house is red. No, it doesn't work that way. So I always tell people, like, if you want to change the knowledge halfway, it's best to embed that knowledge in the database and then you retrieve it and do like retrieval augmented generation is much better than fine-tuning it, because if you want to fine-tune, I'd rather you just pre-train your entire thing with the new data. Don't contaminate old data and new data. It will confuse the model. Yeah, because the pre-training has been done, like, imagine pre-training is like you study all the way to university for 20 over years. And the fine-tuning is like you go to your first job in your first month and they tell you, okay, everyone, forget what you have learned all the way until university. Do this instead. Very hard, especially if it's a motor skill. Like, if let's say you learn how to use the QWERTY keyboard, and now I ask you, I'm going to mirror image the entire keyboard, learn from scratch. You are going to have a hard time. Although I fine tune you on the new keyboard, you are going to have a hard time, right? Okay, I'm giving an assumption here. I assume most people have a hard time. I haven't really tried it, but I can imagine that will be difficult. So same thing. So if you were to just change your training data halfway, your model it will be very hard for your model to learn. Yeah. And back to the steps, if we permute the steps like that, I think it will be difficult for the model to learn as well. So no good answer for that. Yeah, we just have to hope that the distribution for the steps in the training data and the real life is the same. So, you can follow the teacher's steps and still get a good score.
Sorry, can I chime in here?
Yeah, go ahead. Yeah.
Yeah, try to make it brief. Um, the analogy you give on human, the learning the keyboard, the new layout, right? So
Yeah. Yeah.
okay, so basically it's also human also face the same issue, right? You have all distribution thing. It's hard. It's not unique to
Oh,
uh,
definitely, definitely. We are not perfect. Humans are definitely not perfect. Yeah.
uh right. Another one is so on your this 1 plus 2 3 plus 3 these two examples. So if you use self-supervised learning, like the model basically if you fine-tune or train on the red color one, then on the blue color one, even if it's correct, basically the model can't tell it like to the model it has no difference from a wrong reasoning trace, right? Because it is only incentivized to, I mean, to learn from the supervised data. That's why um, even the other one is correct, makes no difference to it. One last point is, uh, so I was thinking because
Yeah.
you mentioned something like, okay, back to generalization. So and reward hacking. So because I was just thinking, maybe the way you want to get novel uh thinking trace or to solve even novel solution is you probably want something like reward hacking because it can be reward hacking basically give you something like completely not expected, right?
Mm.
So it can, of course, it can lead to very bad result, but on the flip side, it also can give you very innovative things. So maybe I was just thinking maybe there's some direction worth exploring. Because in that case, you give the model the freedom to explore different try out new things, right?
How do you propose to do that? How do you give the freedom? Like,
I the freedom is you are criticizing, oh, I only give one number, so the model doesn't know what exactly the feedback. But on the flip side, if you give too specific feedback, then the model will just follow your feedback. Will just conform to what you think is maybe it's correct, but maybe it's just one specific way of doing the correct things. But when you give the model just one reverse signal, then it can try out different things to improve it. Of course, it can lead to the failure mode where it's just simply hacking the reward and doesn't give you any meaningful improvement. But it also can sometimes give you genuinely novel solutions, right? But I don't know, it's of course it's hard to control how to encourage model to give you the genuine novel solution rather than just hacking the reward. But I think certain amount of freedom is needed to get to some to let the model enable the model to learn to generate new novel solution. Yeah. So this is like a small pushback to your view on reward not is not enough, but sometimes you might want to give it some flexibility, some freedom to try out different things.
Yeah, so not giving a definite route to success would let the model learn more paths, right?
Yeah,
So
yeah,
that
in some way, yeah.
I mean there's trade-offs to that. So like if we want to do that, then we don't do SRL anymore. We can do the full RLVR where the rewards at the end, then then these sub steps wouldn't matter anymore because
No, no,
both
no. It
answers
can
would be
still
okay.
matters because the six is still important, but like in this case, maybe it'll try the red path or maybe it'll try the blue path. So even it can explore different ways of getting there.
Oh, okay. So
Yeah.
basically you say you don't fix the expert trajectory. You evaluate the student's trajectory one by one to make sure it's correct separately.
Uh,
I mean,
no,
okay,
my current idea is simply trying to say that given just the reward might have an upside, which is to encourage the model to explore.
yeah, no, because if you look
Yeah.
at the way the SRL is phrased, right? Is framed, the SRL would say that the reward for the first step is 3, and the reward for the second step is 6. So even if we just go by reward without the traces, this 2 here would be wrong because here is 5 and 6. So
Mm.
this reward is
Yeah,
wrong.
then it's just too granular. Maybe this different level you can specify the intermediate reward. You can afford to give it some freedom to explore some for some
Yeah.
sub problem just to let it to explore. So it will not have it will be less prone to overfitting. Yeah.
I mean, actually, what you say is a good point. Like, you don't have to supervise every single step, and you just need to see the main steps. And I think this paper tries to do that. They take away the thinking steps because feel free to explore your thinking step, right? I don't constrain your thoughts, but I do check midway whether you succeeded halfway. So like that's the intermediate rewards. So I think the paper tries to do that, but I think they could do it better.
Yeah,
But
I agree. Like this idea is very high level. There's definitely non-trivial effort needed to make it actually work. Because this a downside is also very obvious, right? Yeah.
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 All right, there's more people who want to talk. Please go ahead. Next person. Yeah.
No, I'm just saying that the self-play, like what you're explaining, the self-play, right? That's a very important aspect. Anyways, Derek, you want to go?
No, I was just listening to the conversation. If we are doing away with the traces altogether and just focusing on the step-by-step analysis, when that requires some type of state tracking. So the either the policy model or whatever encoder you're using to encode the lane encoding, wouldn't that require some form of state tracking so the model can keep track of where it is within the reasoning process in order to be able to explore and branch out in different ways?
Yeah.
Because now we don't have the. I'm trying to understand the JU's suggestion that if we do away with the reasoning steps, we no longer have like a ground truth or a backbone. So now we're going through the step by step to see where we are in proximity or relativity to the objective.
Yeah. So I think I quite like this discussion, and I think like having the model explore different paths without being bound to a preset path is good. And actually, I thought of a way to do it. So the way is very simple. you take the model output of step 1 and then you pass it to LM as a judge, which means like the LM doesn't have a predefined output. It just looks at the student output and says that, hey, this is good or this is bad. All right, then maybe step 1 plus step 2, combine, and then you pass this as L to LM as a judge again. So like we don't prefix that, hey, you must always do like add 1 plus 2 first, then add 3 plus 3. If it so happens that the first step is add 2 plus 3, and the second step is add 1 plus 5, and the LM is capable enough to know both works, the LM as a judge will give the right answer for both. And the student will learn that that's all right. Yeah. So it gives them room to explore. So this is what I call flexible judging. I mean, there's no term for that in the AI literature, but it's a data set that evolves with the student. Like, let me just put that here. Data set that evolves with the student. Because we don't give the model answer and then we try to force feed the student into the model answer. Rather, we learn at the student's pace and we correct the student based on what the student knows. Actually, that sounds like a teaching philosophy, right? I quite like it. I quite like it. Because in most modern education, we are just trying to mold all students into the model answer, and that, to be honest, is causing a lack of creativity. And I think that needs to be changed. Yeah. So towards a more individualized learning, more flexible learning. Yeah, I think that's great. I wonder how this would impact LM's performance. Like maybe after this, it would be able to solve more questions because it doesn't need to feed into the more of the training data anymore. Yep. So yeah. Okay. So yeah, Robert, you sent me a link on reinforcement learning from AI feedback. So that is what Anthropic did. RLAIF, reinforcement learning from AI feedback. And basically the AI will give feedback in the form of a criticism. And then the model will learn how to incorporate that criticism and improve its data. I actually like this idea. Provided the AI is capable enough to give the right criticism, this actually works better than reinforcement learning. If correct me if I'm wrong. Yeah, the AI feedback should be a criticism, not a reward score. So
Absolutely. I think because we don't learn, you said we don't learn as anything like in life, you only learn from your mistakes. And if you constantly follow in the wrong path, like just as a human being with our biases, we find out that we become extremely stuck. And that's a very problematic, way to look at things.
yeah, very nice. I think we uncovered quite a lot of ideas here. And I really like the idea that your data set evolves with the student, because then we don't have to fixate the student on one data set. I mean, without this discussion, I wouldn't have come up with something like that. So yeah, great discussion. Yeah, so this was what we talked about last week, that the reward here is not that great. It's just based on the rule-based matching of blocks, which may not capture the semantic meaning. All right, so let's take a look at how SRL looks like after you have done the training. So let's say this is the input prompt, like what is the least positive integer value of x for which this inequality 3x greater than 2x plus 1 is true. So by default, the model will come out with a thinking token because that's how it's trained. But the model will only be evaluated on the answer tokens or the step tokens. So the first step, they simplify x equals x greater than 1. Then they do another thinking step again. And then after that, they do to 6 greater than 5. And hence x equals to 2 is a solution. And so the least positive integer is 2. So you can see that this entire thing is something like your LLM has learned how to do step-by-step reasoning, okay, without even the need of a moderator or like a overall orchestrator agent. Okay, because usually how this is done is that in agentic systems we ask the LLM, like the agent or the orchestrator will task a mini LLM to to solve something. I mean, the tool could be an LLM call, and the tool would solve one step. And then after that, it will go back again. Okay, and then you ask the LM call to solve another step. So this is how it looks like in agentic systems. It kind of augments the LM capabilities because a single LM maybe is great for one step, but it may not be able to hold long context and so on. So this agent will then ask the LM to do specific steps. Okay, here it looks like an agentic workflow, to be honest. It looks like an agentic workflow, especially in the React framework. So a lot of jargon here. So React framework is the reasoning and acting framework, which kind of makes the LLM like be better attuned to the environment. So what it does is that you have an observation from the environment, and then you have your thoughts, and then you have your actions. I really like this framework because like based on the observation, it's like these are the previous steps. Your thoughts could be next step is it's better to do something, and then your action is to do something. So this works really well for LM reasoning on like embodied systems, and also works pretty well on math data sets because you can reason on a math problem and think of what to do based on what you have seen before and come up with action. It seems that this entire training model of SRL has made the model become something like a React agent, like without the agent part. Like this is just an LM output, and it already conforms to a React agent kind of style. I really like the React framework. Very nice. Objects, thoughts, actions. So if you are in the military, you would know the OODA loop also. Orient, uh, observe, orient, decide, and act. So this is a very nice model of thinking where you see what has gone on before, you think about what you should do next, you decide on the action, and then you act on the action. So simplify is observations, thoughts, actions. So this really looks like observations, thoughts, actions. So if you look here, this thinking is the thoughts. This like previous context is the observation, and this is your action. So it fits very naturally in this loop. And the reason why agentic systems can work pretty well is they also conform to this loop more or less. So SRL seems to be a pseudo agentic trainer, right? I like the way that it looks like in the end. So if you look at another example of a coding agent, so a coding agent is let's say you want to fix a certain issue like this origin validator not properly handled. So you do step one. Okay, first this is basically the thoughts. Let me just highlight for you all. So observation is this. This is the thoughts, and these are the actions. So the action is more or less a function call, right? So you see, it can lead to a function call. So, if you were to wrap your action in a function with parameters, essentially this is an agentic structure already. You just need to extract out these parameters, run the function, provide back the observations, provide back the function output as observation of next step. So can you see that this easily fits into an agentic structure where you take an agent, you call a tool, okay, get back the result, you call another tool and so on until you complete your task. So SRL training essentially trains an agentic agentic LM, which is really cool. So later we have a discussion question also, like, is it better an agentic system to do this, or should we just train the LM to perform the agentic system's roles, right? But before that, I have something that we need to discuss, and it's something that has bothered me a bit. And this is basically not training on certain tokens are good. So just now we saw not training on thinking tokens is a good thing, right? Because I think, all right, the model can get confused. Okay, one thing is that in the thinking tokens, they might actually think that they have done a certain step. I've seen that happen, and then they forget to call the tool because they thought they have called the tool. Like they think, oh, I should call Google search, and the Google results return this. So they might already call the tool and so on. So this is one reason why thinking tokens is not that great. Another reason is that it may overfit to the framework and not the essence of the thoughts. Like what you have seen just now, like it doesn't get the result. Like sometimes it might think 1 + 1 = 3, but because like it fits most of the thinking tokens, like 1 + 1, it gets away with it. Yeah, so thinking tokens might not be good to train on. Another reason, like what Zeri mentioned, is that you give the model flexibility to explore different routes of thoughts without conforming to model answer. So there are a few good reasons for not training on thinking tokens. Quite revolutionary, actually, like quite revolutionary, because all along we've been telling us, lots of papers have been telling us that you should bootstrap on your reasoning. You should use your reasoning tokens to create new data sets and train on those data sets. So that apparently only works if you have a lot of data. Yeah, because in this paper, they only use 1,000 data sets, and it really made the model worse. Yeah, so I mean, if you have lots of data, you can use any approach, but if you have not many data, maybe we have to use a smarter approach, right? So not training on thinking tokens may be a smarter approach, right? So you can see that this is how we have the prompt, and then this is my output. I don't train on all the thinking tokens. I only train on the answer for each step. And even in this paper, the answer is not trained by supervised fine-tuning. It's trained by reinforcement learning. It's trained by reward matching of predicted answer to model answer. Whether this is the right approach, I actually don't think so. I think it's better to train on the model answer directly. Give the model answer to the student. Yeah, so there's some room for improvement here, but not training on the thinking tokens. I think quite interesting. But can we do more? I think this is my personal opinion. I think we also should not train on the output of a tool call. All right, because I have seen large language models hallucinate the output of a tool call. So for example, you call a tool and then you get the output. So for example, your tool is to call a Google search. And then there are some LLMs that just report the output of the search without even calling the tool. Okay, don't laugh, right? This actually happened, okay, especially for weaker LLMs that are trained, like they tend to just hallucinate the tool call. And I attribute this to being fine-tuned on the tool call response as well. So it thinks that it can generate the tool call. So yeah, I mean, sometimes it might even hallucinate calling the calculator tool and actually just use its own internal LLM logic to calculate stuff. So that's not something that we want. So I honestly think the output should not be part of the training tokens. Like you shouldn't train on the output of your tool call. The output of the tool call should be sacred, should put one side. You can use the output. Let me put here. You can use the output of a tool call as the context of LM, but never as the predicted tokens. Okay, never. All right, because LMs will overfit to what it's predicting. And you don't want it to predict the tool call output. It's not healthy because the LM might think it's part of the tool call. So yeah, this is something that I've observed with smaller LMs, like maybe the larger ones, they are smarter not to do that, but this still happens. So training on reasoning traces might be good, but it comes with some downsides. And I really think that, we shouldn't train, not just, we shouldn't train on the thinking tokens as what the paper mentioned. I also don't think we should train on the output of the tool call. All right. Yes, please go ahead. Any questions, discussions?
What about training on self-correction?
Then that will be the output of the step. Because self-correction, in the end, like you could say that, oh, my earlier step the output for your step. Yeah. So I mean your thinking might be that, oh, I should do self-correction, but your step itself will reflect like the earlier 1 + 1 = 3 is incorrect. Something like that. I just put it somewhere. Your step might be something like that. I change it. It should be 1 + 1 = 2. So that could be your step output. So self-reflection, I think, can still be trained on, but you don't have to train the thinking token. You also don't have to train the output tokens for the function call. Yeah, does that make sense to you? Like I think self-correction can still be okay, can still be learned. Okay, yeah, I'm just gonna assume that is all right. Yeah.
One
Yes, sir.
comment on still using the two call result as a context. Actually, there's one blog which I just shared from Minimax. Argue that's actually very, very crucial. Yeah.
Oh, did they also discover this same thing?
Oh no, your main point is not to train on the two calling result, which I do agree. I think that you're correct. But you also mentioned it can be used as a context. But I'm just saying that there's one like Minimax has a blog article on arguing that it's not just you can, but it's very critical. Yeah.
Oh, you must use that as a context, right? Then
It's
you know what
very,
to do
yeah,
next, right?
according to them, it's very critical. And they observe that I think entropic, or I think it's entropic. Then they did some study on that, find that's extremely critical for the performance. Yeah.
Yeah, I would think so, because the tool call output is part of your observation of the world, right? If you don't put the observation, how are you going to decide what to
Oh,
do
no,
next?
no. No, it's like, usually just to preserve the context window, because this very limited, especially thinking token can be very long, right? So I would say, naively thinking, if you ask me, I would say, oh, maybe then because the chatbot, like you want to optimize the user experience, you probably don't want to, for the following subsequent conversation within the same, sorry, the dialogue within the same conversation, you probably don't want to include the reasoning trace of your previous conversation. Sorry, for your previous round of dialogues, right?
You know what?
Because you have a very limited context length. For one conversation, you usually, if you ask me, I would say you probably don't want to do that, just to preserve your context window. But they argue that actually you do need to include the reasoning trace of all your past uh, conversation inside, and I think they argue that because entropy, they don't have such a feature, and they create some problem. You can have a look at the article if you're interested.
Okay, yep. I'll take a look at the Minimax article. Right, shall we move on? So let's move to the next slide. Okay, so where's the next slide? Yes. So now we come to the issue of expanding beyond the expert, all right, because I mean, while an expert is there for most cases, humans have many experts at different domains. Some problems lie beyond the domain of expertise, like it just has not been explored. So you may not have access to an expert for like LLM as a charge, or like you may not have the expert trajectories to train your model on. So in the supervised reinforcement learning approach, we assume that the expert is always there with us, and the expert can handhold the student model into doing the right steps. Okay, but what if there's no expert? Right? Let's think about it. What if there's no expert? Right, which is a very practical problem, especially for domains that are new. Like for example, you want to do deep research, maybe. Like how do you know what is the correct article to search for when the topic is something that maybe you haven't seen before? Yeah. Or you are talking about exploring a maze, maybe. And how do you know where to navigate to when you don't even know what maze you are in? Like, I mean, it could be a different maze. So if we have this kind of thing, the expert is not going to help much, you see? Like the expert doesn't even know the maze. Maybe the expert may have some rules or guide to explore any maze, like certain kind of. So there's one way to still utilize the expert. Yeah, I didn't put this as a bullet point. Like the expert can still have some guidelines or heuristic as to how to tackle different problems. So you can maybe still use the same guidelines. Right? So that's one approach to use an expert. So that actually is probably how we should use AI tools. An expert can distill down the thought process, maybe like observation, thought sections or something. That could be one framework. Use that framework to solve different problems. And I've seen most of the more promising AI solutions are actually formulated with an expert doing the framework at the back end that actually make the LM output a response that's quite coherent and relevant for the industry. So that's one way to use the expert. But suppose that even the expert has no framework to solve this problem because it's just too new and novel. So how can we solve this problem? All right. So we need to solve it using some traditional like exploration techniques. And to be honest, humans are actually not bad at exploration. So like one way to see human exploration, I like to always use this example. It's like food, all right? So maybe one day you want to eat prata, and then maybe there's maybe another food, maybe cheesecake. You maybe ate prata your first day, and then you have a tummy ache, and then you may not want to eat prata for the next 5 or 6 days. You also eat the cheesecake. But after a while, it might be like, maybe that tummy ache was not the fault of the prata. Maybe I'll try it again. So at day 7, maybe I'll go back to the prata again. So, you humans tend to explore, exploit naturally. So we tend to want to explore new areas, like we like to explore new areas, but of course, we don't explore all the time because like sometimes you want to stick to things, and this is actually subject to individual preferences. And also as a group, okay, as a group, humans explore different topics at different rates. Okay, so like research, now the trend is LLMs. Maybe next time it will be something like world models, JEPA, and all that kind of stuff, like Yan LeCun. So we tend to have explore, exploit in an individual setting. We also have the explore, exploit in a group setting. All right, so there are different ways to do this explore, exploit by making you a bit more curious to explore new areas, or making you a bit less curious, and you can have a mix of personalities, and all you can put all of these different agents in the maze with different personalities. Maybe they share information with one another, and then collectively as a group we could learn. So I think that is my most promising idea so far, is different personalities, multiple agents to explore. So I think that's how we learn as well as a population. All right. Or like if you don't have the expert, you can also try to reformulate the problem to a sub problem for easier solutions, which means that it's similar to having the guidelines by the expert agent. The expert agent tells you like how exactly to break down an ANSI problem, then you maybe solve by parts that you are more familiar with. So expert is still there. It's just perhaps not in the model answer. Like, because maybe the expert doesn't have the model answer as well. The expert only knows how to do a certain way, and then you still need to do the model answer, do the cool call yourself. The expert has no knowledge of all this, but they know the rough idea of how to do it. So yeah, we cannot just use SRL if we don't have the expert trajectories, especially if your expert doesn't have access to the tool call, then how is it going to generate the trajectory for you, right? So that's something that we need to think about. So there's some explore exploit that needs to be done here. Later I'll talk about how I think we can do it. Okay, yeah, Robert, you want to say something?
Yeah. So if you're doing, let's say, like tree of thought, right? And then you basically go to the point where the model finds a new problem and solves this new problem. Do we reward that, or do we just exploit it? Like what happens in that case? Because that's what happens with humans, right? Then that one new basically discovery leads to another discovery. But
Yeah,
do
I
we
mean,
reward it?
you can probably reward each node of the tree when you discover it. Yeah, I mean, but then if you just reward based on that, the thing is, how do you know whether it's ground truth? Like in the tree of thought, like you kind of still need to curate the branches, right? Before you go to the end point. Like let me just draw out tree of thought. Tree of thought is like you have a starting state, and then you have maybe three variations of possible next states, and then maybe at each step you curate, you filter away, and then like based on whether which one is more promising, you generate another tree. Is this tree of thought? I mean, I think this is tree of thought. Then after that,
Yeah.
you filter out the next steps, and then eventually this one might lead to the answer. So this is tree of thought. So like tree of
But if you
thought,
find it, yeah.
you
But my question is, let's say you answered though inside here a whole new problem that you weren't thinking of, but then that usually leads to the right answer
yeah.
on
So
these.
where do you want to put the reward for this?
That's right. Oh no, that's what I'm thinking. I think we have to reward the model for solving problems that are irrelevant to what we asked. I just don't know how.
I think for tree of thought, it's very dangerous to put the reward at the branch over here. Like if you want to reward this node here, it might turn out that you're rewarding the wrong node because you haven't seen the answer yet. So yeah, if you reward this, maybe you might explore the wrong path, and maybe there's a node here that actually leads to the answer, then you're gone. Yeah. Or you don't generate the right trajectory, you will never reach the node. So I think for such cases, it might be safer to reward the end goal, but same thing for the RLVR problem, you might never reach the end goal. So I think especially for this kind of like multi-step problem, it's very important to reward differently. Like later you will see my goal-directed learning approach. I think it's possible to reward failed trajectories as well. So I like the idea you can learn from both failed and both successful trajectories because you learn a lot more signals like that. For the exploration step, you just have to leave it to different personalities to explore different parts of the tree. Yeah. So I later that I explain what the goal-directed learning I have in mind looks like. Then maybe we can discuss more on that. But for tree of thought, I really think there's no easy way to reward middle of exploration because you don't know whether it's correct. Yeah, if that makes sense to you, yes. Okay, so let's move on to the next point. Like many real-world problems have dynamically changing solutions, and if you use a reward-based approach, you may not learn correctly because like maybe in 2025, if you say RL is great, maybe your reward is like 1. But in 2026, if you say RL is great, maybe your reward is 0.5. And then like you spend years learning the RL, maybe not 2025, maybe like 2017, I guess, like when is it 17 when AlphaGo won? Yeah, so like if you learn the same topic, same action, you may get different rewards over time, and then you have to relearn the rewards every time the environment changes because your reward is a proxy of goal attainment. So if your pathway changes, if your goal changes, you have to relearn all the rewards again, all right? Or at least the rewards that are affected. So I think learning by rewards is good if your problem is small, like a motor control problem, like how to move your hand to balance it, that may be okay because your hand kind of fixed. I mean, it rarely happens that you lose a part of your hand, but you can learn that again. Because then that part is fixed again. So you don't it doesn't dynamically change that often. So RL works for that kind of problems. You don't have to keep relearning your rewards. But in real world settings, if you need to keep relearning your rewards because the environment has changed, like you navigate a maze and suddenly the maze, the gap shuts off. You cannot navigate there. You have to relearn the entire maze again, or at least the parts that are affected. So that's not a very good way of learning. And that's why I think we need to do something like goal-directed learning. It's still a next token prediction in some sense, but we are predicting the next action based on what has actually happened. So let me illustrate this. So this is an idea that I came up with like 3-4 years ago. I spent my whole PhD thinking of it. And I think it's very similar to goal-directed learning in the brain. We do have some goal-directed learning, although most people talk about the reward-based learning. I think goal-directed learning is very important. Okay, let me give you an example. So this is my starting state. Then I take an action. Then I have a new state, take an action, and then I take the final state. So what are these states? These states could be something like you are at home. Action 1, go down the stairs. What's my stage 2? At floor 1 of my house. Okay, then maybe your next action could be like take a bus, and then maybe you reach school. So these are the steps. There's no right and no wrong. I take a certain action, I transit from a state to another state. But what have we learned from this? What have we learned? We have learned that in this trajectory of 3 different states, okay, I did not just learn like one action like that. I mean, in SRL terms, maybe I learned how to predict this one time, and then this is maybe data set 1 and this data set 2. Okay, so maybe we learned that in like SRL context, but we actually also learned something else. We actually also learned to get from this part here to this part here, we also learn something. So like SRL is like halfway of this thing because it learns the rewards, okay, for like each intermediate like state. Here we actually don't need the reward. Okay, here what we just need to learn is if we want to get from state 1 to state 3, then do action A1 first. If you want to get from state 1 to state 2, also do action A1 first. And then if you want to get from state 2 to state 3, then do action A2 first. So can you see just one short trajectory like that? I learned 3 different actions to get from a certain state to a certain state. So now let's reframe this a bit. Okay, because right now we from a certain state to a certain state. Right now, I just say my goal is state 3. My current state is state 1, or it could be and then my next action could be A1. Or this one over here, your goal could be S3. My current state you can say that I've transited from state 1 to state 2, and then my next action is A2. So with just like one trajectory like that, we have learned so much. We could learn so many different intermediate trajectories, and each of them predicts an action. And this action, if your environment doesn't change, you don't have to relearn the action. But if your environment changes, you might need to relearn the action. Like for example, if let's say you're in a maze like that, okay, and then initially you get out by going here. Up here is the exit to state 2. Okay, but let's say that is blocked. Maybe we need to use the other path to go to state 2. Let's say this is blocked. We might need to use the other path to go to state 2, which is like this path. So you might need to change your next action. But I've done some research and I've kind of shown that if you just change your next action, you learn faster than changing the reward, because it's harder to learn the reward than to learn the next action, right? This learns very, very fast. So instead of doing reward-based prediction, why not do action-based prediction? Then, it would be much faster to learn. So that's exactly what I was thinking of. And so this is in the paper, Learning Fast and Slow. Feel free to check it out. I think this is my best paper actually. But unfortunately, I haven't really followed up on this. Maybe I should, with an LLM take on this, because this was done using neural networks, inspired by a hippocampal replay in mice. So there's always a hippocampal. This is the pre-play and this is the like simulated play, because like this is what the mice has been through, the previous states all the way to the current state, and then current state backwards to the previous state. And this is what the mice imagines in his head, like current state to the final state and final state backwards. And my thought process is that you can learn from any state. Like you can learn from the pre-play and the future play. You can learn from any start state to any end state, and you can learn the first action, like even for the predicted play. Because if you can predict it and your world model is good, you might as well also learn from that. You don't waste your look ahead tree, like, because you can do some simulation planning. Don't waste that. So we know this trajectory A, B, C. We also know how to go from A to B, A to C, and B to C. So essentially, the neural network takes in the state, the goal, and outputs an action. This is when I did it, it was a neural network where the state is like integers, goals are integers because it's a grid, and the action is also an integer, up, down, left, right kind of thing. But over here in the neural network case, your state could be a set of context. Your LLM context could be the state. Okay. Sorry. It could be the trajectory of what has happened. So it's something like in the SRL, I put all my previous steps there. My goal is maybe my overall context of like all the problems to solve, and my action could be the next step. So essentially, we could do what SRL is doing. We map it over to this goal-directed learning, and instead of using reward, you actually kind of like fine-tune onto the next step. And if we talk about like not training on the thinking or output tokens, it's fine, because the only tokens we are training on are the next step tokens, and everything else actually goes into the trajectory. Yeah. So you will never be predicting tokens that are not thinking. You'll never be predicting thinking and output tokens. You'll just be predicting next step tokens. So yeah, I do hope to implement something like this on a data set. So if you're interested, let me know. We could do something together. So this goal-directed learning is something I spent 4 years thinking of, and this is what I came up with. You predict the next action based on a state and goal. Simple as that. Yeah. You can always adapt it to the LM. Okay, any questions? Or like, does this look familiar to you? Have you seen this before?
Yeah, I read it not too long ago. It's a fascinating read.
Oh, you read my paper, is it?
Yeah, just like after the last call when you said it, I had to read it. And there's a lot of physics that support this, and like Tesla, there's Nikola Tesla, there's a lot of interesting things here that I'd love to share with you. Not on this call, but definitely another
Oh,
time.
yeah, definitely. Yeah. So I'm actually looking to continue this line of work. I'm just looking for the right data set to use it. So if you have any suggestions, let me know. I do think we could fine-tune an LLM to do this approach in something similar to what SRL is doing, because SRL, they also dissect the whole problem into sub-steps. But for SRL, they use reward. But here I think we could just use the next step. And what's the benefit of doing this next step? The benefit is you have no need for LLM as a judge. You don't have to use 5 million or 10 million calls to rank how good it is. You can just use the next step and you give the model answer to the student because you tell the student what the next step is. You don't need to give a reward then and ask the student to like guess whether it's good or not. Like I'll guess what's the right answer based on that reward. It's so hard. You give the model answer, the student learns way better. Yeah. So yeah.
I think block diffusion is something you're gonna really like.
Oh yeah,
And
looking
if
forward
you
to that.
like this, like if this is your baby, I think block diffusion is your answer for what you're doing.
Nice, nice. Yeah. So I hope I convince you that this model is good. I think it's a really nice model. In fact, JEPA, the Yen-LeCun JEPA, the Joint Embedding Predictive Architecture, Joint Embedding Predictive Architecture, it's in a similar vein. You have a start state, you have a goal state, and then you predict like the action. In this case, the action is like in this case, these are in JEPA, the start state and goal state are latent space. Okay, and your action itself, maybe it's like which blocks are masked and which blocks are not. Or the action could be like the output of your latent space. Yeah, so it's in a similar vein. You have a start state, a end state, and you predict something. So you need to predict something in order to learn from that prediction. Because if you don't predict something, you have nothing to learn from. But we don't predict reward, we predict an action.
There's a thing called least action principle, or like law of least action, or least action graph. Like this is what you're building is a least action graph. If you get into it and like deep into it, that's what this is.
Nice, nice. Yeah. I think this idea definitely is not like new per se, but it's something that I converged to after it's something I converged to after I tried reinforcement learning for 4 years and I didn't quite like it because it didn't learn as fast as I thought it would. Yeah. Okay, so yep, I think let's go to the discussion section now. So let's talk about the first question. So, like, should we factor in reward for thinking tokens as well? So just now, Terry and I, we talked about it. Yeah, it's possible to do that. But maybe it might be restrictive or like constraining to the student model to learn from a fixed way of thinking. That's one disadvantage. The other disadvantage is that it might overfit to the structure, but not the essence of thought. Because like you can overfit to a framework like first, then finally, but your answers are all wrong. But you still get quite a high reward because your token match is high. Okay, unless you use LM as a judge, then maybe it might not just overfit to the structure. Okay, this part here it can be mitigated if you use LM as a judge. Okay, but I think overall it still may not be that great, and I also don't think you should train on the two output tokens because you might hallucinate the two call without even calling it. Okay, anything else to add for this? I think we more or less discussed this just now. All good? Okay, next is reward matching based on subsequence a bit too restricted? Yes, okay, we discussed this last week. So LM as a judge might be able to have better understanding of the semantics, okay, rather than just using token matching. Because token matching, you can match very, very similar things, but you call it wrong. Like for example, if you call it, your model answer is your model answer, it was great. Then the predicted answer maybe is it awesome, very good. Then you see that both are actually the same thing, but there's a zero match because they use different words. Okay, same meaning, zero reward. So subsequent matching is actually not that great. Maybe that explains why their SRL did not do that great because if you look at the step output for SRL, it's very, very long sentences and not all the time your sentences are going to be the same as the model answer, especially if we don't give the model answer to the student. The student in SRL just sees the reward signal, okay, which is like a number, like And I think it's a number between -1 to 1. And it's very hard to learn from a number. Yeah, it's very hard to learn. So I think if anyone from Google SRL is doing this, consider giving the model answer as well. Don't just give the reward, Yeah. Okay, let's any questions or any thoughts on this? Okay, next question. Should we train the LLM to do multiple steps of reasoning natively or use a reasoning framework over LLM? I think this is a question that I'm half. Like I think it's okay to use the LLM to to do the thinking steps. But I also think that it might be better to have a external orchestrator so that you can, stop the model halfway and do something else. So I think both are okay. Just need to know when to stop the model's output to do something else. Because, if you were to do a two call, you need to pause LM generation to do it. Yeah. So it might be more intuitive to use a reasoning framework. Yeah. Robert, you want to say something?
Yeah, I think there needs to be constraints, 100%. Because if you think about it, like an environment is a constraint, right? I mean, gravity allows me not to fly. Like you can't always, you have to have some constraints here, which I would like to research more about before I give answers. But I definitely believe there has to be something.
Yeah, definitely. So I think this is something that I'm actually open to both. As long as it works, it doesn't matter the method. In my mind, I just go by empirical results. If it works, I'm happy with it. So I think both work. So I'm happy with the way SRL does it. It omits the need of a reasoning framework for simple problems like math that you can use the LM to evaluate the results for simple math addition and subtraction. But once it gets more complicated, you kind of need to pause the model and execute it. Then the SRL approach, you just need to stop generating once it calls a function, and then you recall it after the function is out. So you kind of still need to do the reasoning step for the reasoning framework over the LM for SRL with function calls. But I mean, it kind of helps to have the model natively output a React framework already. I quite like the idea, okay, because React framework is quite nice. So I think it's okay. I think it's okay to actually train the LM to do like React framework based methods. Yep. Okay, so any other comments on this, or good to move to the last
Isn't
one?
isn't that where the Minimax paper came in too, though? That allows a lot of basically like testing to show that it's important to have the model to basically sense or like some level of thinking, like scoring the thinking.
Yeah,
Because if you
definitely. Yeah, I have to read the Minimax paper more to figure out what you are talking about. But I think this level of more reasoning for the model is probably better, like for complex tasks. Yeah, but for simple tasks, maybe over reasons. Yeah. So there's still a pros and cons here. Yeah. So yeah, last one is how can we integrate goal-directed learning and exploration into LLM training? Actually, this is kind of like my life's research already. I think we should do goal-directed learning because goal-directed learning, you learn actions. You learn actions based on your own trajectory or other people's trajectories. And it's you can learn from success and failure because there's no failure in goal-directed learning. You just let me put this again. This is like a soundbite. There's no failure in goal-directed learning because you just learn with a different goal. So let me give you an example. Let's say you are learning how to walk. Okay. So you want to try to learn how to walk. Okay. But okay, maybe not walk because this is a motor action, right? Let's say you want to go from home to school. Okay, but you kind of failed in doing that. Like you took a bus, or you took the stairs, and then you end up at level one. You didn't go to school, but you are supposed to do this like home, stairs, level one, then bus, then school. Okay, you're supposed to do that, but you kind of ended up at level one, but you didn't know where to go to go to school. But it's okay. School was your destination, all right? But you failed to go there. But does that mean that what you have experienced is to be discarded, like what we do in RLVR? We just like this experience is useless. You didn't get anything. No, we just basically say this level one is my goal now. So you just reframe your goal and learn from it. So every experience is a learning experience. You don't waste any experience at all because you can always convert your goal backwards. Then some people might ask me, like, what if you don't reach your goal? Oh, that's fine. I mean, eventually, maybe you have an expert trajectory that you can learn from that brings you to the goal, like school. Or, you might never reach it at all, and that's fine. Maybe you just change your goals. Yeah, so like in life, a lot of times we want to get something, but maybe we can't. Does that mean that we are a failure? Not really, right? You just have to adjust your expectations, adjust your goals, and go for manageable goals. So I don't think all agents will reach the end goal, but that doesn't mean that they are failed agents. They just, optimize for a different path. But eventually, if we have enough agents, okay, this is very important. If we have enough agents with different characteristics, life experience, okay, with the occasional knowledge sharing, we will all progress together because we will all be able to do like harder and harder things together because there's more exploration. Okay, and it's very important. I want to emphasize this. I've emphasized in some of my other videos also. We don't want complete knowledge sharing. Okay, because the moment we have complete knowledge sharing, everyone becomes the same person. All right, and that's not what we want. That will minimize exploration. We still want everyone to be diverse, but we still want knowledge sharing, maybe within interest groups that are aligned in the same direction. Then they all can progress in this direction better because they share knowledge. But don't contaminate this knowledge with other people because we still want other people to explore here. We don't want everyone to explore this. Like you don't want everyone to explore LLMs, but for those people who are exploring LLMs, we want them to share knowledge so that they become better at exploring LLMs. But we still want to keep the other paths open. Yeah. So I think once we can model all this population-based learning, goal-directed learning, we will create a self-adaptive and learning system, which is my aim. Yeah. So I think we are on track to doing that. Yeah. All right. So yeah, I would like to just end this part here. Any comments, questions for this last question?
I have one just about so when you say overlapping skill sets or overlapping basically knowledge, but what about when it comes to like a hive mind? Because the way that a hive mind works, if you look at like bees or anything like that, they all have their own, they don't overlap at all. They're actually very unique creatures to study because they don't do, they do only their job. They
Oh,
do
okay.
not overlap.
Yeah, that would be great also, like specialization, right? You always have a role, but bees can also change their roles sometimes. Or is it ants? Like if there's not enough worker ants, some can convert to worker ants. Yeah, so I think some form of roles are important also. But the roles may not be fixed through life, maybe except the queen bee or something. Yeah. You have to study more. But definitely if you have different roles to play with different kinds of characteristics, that would give the population like quite a distinct characteristic. Like maybe because of the distribution of your population with different characteristics, you can solve a certain problem. Yeah, so I mean, it's similar in that sense. You don't contaminate knowledge. Maybe it's the same as you have species variation within the species so that each does a different job. Yeah, possible. Yep. Okay, last point. If not, I'm going to conclude. Okay, so let's conclude. So I think supervised reinforcement learning is quite a nice idea where we learn step by step, but more needs to be improved. We probably should give the model answer to the student at each step. We also probably should be, seeing how we can reward the student for exploring new middle steps that may not conform to the teacher's response but are still correct. So maybe we might want to look at something like this kind of goal-directed learning where you just make every explored state a goal, and then you can learn from your start state to your end state how to reach there. And the next step could be like the action. So we actually learn better and faster. So yeah, I'll just end off here today. Thanks for discussing and see you all again. Okay, bye. Hang on.